just in case you're wondering if there's any mathematics behind this, I'm just going to show you the number of solutions to the Schroedinger equation. And you can see right here in this column the symbol psi, which of course represents the wave function. So here are mathematical solutions to the Schroedinger equation. And on the left-hand side here, you can see n equal to 1, n equal to 2, n equal to 3. And as you'll find out, this is the principal quantum number, but essentially it means those different energy levels that Bohr was referring to. Instead of just thinking about an energy level and that electron just exists in that energy level, we're going to start to be thinking about sublevels. Where does that electron exist within an energy level? What particular sublevel? And those sublevels are associated with different shapes of boundary surface diagrams and different orientations in space. So let's start to unpack this. This is a diagram in your course pack found on page 112. There's a lot to unpack here. And one of the things that I often will tell students is as we unpack these things, at first it might be hard to pick up on the trends. I liken this to if you were to, for instance, come across a group of friends and they're playing a game of cards or a board game, and you're invited to join them. Everyone else knows how to play and you're trying to learn how to play. And so gradually they let you in on the rules. At first you're confused. You see someone shout and get all excited because they just won something, and you have no idea why they're doing that because you don't understand the rules yet. Well, there'll be something similar here if you haven't seen this before. At first, you may not understand the rules or the patterns, and then they start to unfold and come together and gel. And most students do come to at least be able to work with these various rules. Again, these rules are mathematical rules as defined by the solutions to the Schroedinger equation. So at the top here, I define 3 quantum numbers. As you're going to see, there are 4 quantum numbers in the end, but we'll just deal with 3 here. You're already aware or familiar with that first quantum number, n, and you're already familiar with, in fact, that n can have an infinite number of allowed values, but they're discrete integer values. So 1, 2, 3, 4, etc., all the way up to infinity. N represents, in part, the size of our orbitals, in turn boundary surface diagrams, and the energy of our orbitals, and therefore the energy of the electron. L, which represents the angular momentum or azimuthal quantum number, tells us about the shape of our boundary surface diagram. It's often referred to as the subshell. And you'll see that we're going to have a certain mathematical code for the different values for L, and that in turn they represent some symbols like S, P, D, F. And as we will also see, the azimuthal quantum number does represent to some degree the energy in multi-electron atoms. So I'm getting ahead of myself here, but right now we're only focusing on the hydrogen atom and that single electron. But you'll see that these same organization patterns will be applied to multi-electron atoms. And then finally, ML, which corresponds to the orientation in space. So how those boundary surface diagrams are oriented relative to one another. So let's start with ground state. And this is n equal to 1. And instead of just saying, oh, there's an electron at n equal to 1, we'll say that an electron exists in the 1s orbital. So it exists in that boundary surface diagram represented by the sphere. Now we can represent that condition by 3 quantum numbers. So n equal to 1, and in turn L equal to 0, and ML equal to 0. Now right now you may have no idea how we came up with those numbers. N is equal to 1, which means the first energy level. So maybe that's okay. But L equal to 0, as it turns out, the subshell value, the angular momentum or the azimuthal quantum number, its value is determined by n. And so you can see it here in the rules, or allowed values. L is equal to, once again, a series of integers all the way up to n minus 1. So if n is equal to 1, as it turns out, then L can only equal 0. So that's, in a part, a mathematical solution. And what's the significance of L equal to 0? Well, here in the chart it says that if L is equal to 0, then we're talking about the S subshell, that spherical orbital. Now, unfortunately, S doesn't stand for spherical. It actually has to do with some spectral lines and things, but I need you to associate that letter S with a sphere. And the orientation in space also equals 0. Now, right now, it will be confusing for you to know where the ML value comes from and the significance. But for now, ML equal to 0 essentially is telling us that there is no particular orientation in space. If you think about a sphere, there really isn't a particular orientation in space, especially if a sphere is perfectly symmetrical. So bear with me with this ML equal to 0. Let's look at the second energy level. I've made my drawing so that it in fact represents, at least in some way, the differences in energy between n equal to 2 and n equal to 1, and n equal to 3 versus n equal to 2. You may remember that the biggest jump in energy for the hydrogen atom and for other atoms is that 1 up to 2 or 2 down to 1, and all other changes in energy are quite a bit smaller, between 2 and 3, 3 and 4, and so on. So this is why I've left that big space between n equal to 1 and n equal to 2. So now let's imagine that the electron has been bumped up to the second energy level. So the electron's in an excited state. Unlike the Bohr model, we're not just going to say, oh, the electron's at n equal to 2. Rather, we want to specify, is it in an s orbital or is it in a p orbital? And you may say, wait a minute, where did the p orbitals come from? Okay, so let's see how those quantum numbers work. Now we have n equal to 2. So going over to our angular momentum or azimuthal quantum number, you can see that L is equal to 0, 1, 2, all the way up to n minus 1. So if n is equal to 2, this means that L can be 0 and 1. And so there are two possible values for L, 0 and 1. You'll notice that I'm representing some of these quantum numbers at the top of the table. N equal to 2 can have L equal to 0 and L equal to 1. And so I'm showing these solutions. As it turns out then, ML can have certain values. So ML can equal to 0. In a sense, we already saw that in the previous example. But what about for L equal to 1? Well, ML can be minus 1, 0, and 1. So the idea here and what's meant by these allowed values is you look at the L value, and it can equal the positive or the negative version of that L value, and then you climb up to 0 and then up to that L value. So once again, if L is equal to 1, then ML can be minus 1, 0, and 1. So this means that for L equal to 1, there are 3 different orientations in space. Now, what does that L equal to 1 mean? Well, it means we're dealing with the P sublevel or subshell. And represented here in our diagram, we can have the p orbital oriented in the x orientation or x-axis, y-axis, or the z-axis. The shape of a p orbital is different than an s orbital, and we'll show those shapes in a minute. Before we go on, though, I'd like you to start to organize this information. So I ask you to turn to page 117. And in a sense, we're going to represent everything that's on this page in 117. And you'll have access, of course, to page 117 as you're doing your assignments and tests. I think you'll find this page is a good summary. So let's take a look. Again, principal quantum number, n equal to 1. The azimuthal quantum number, therefore, can only equal 0. The magnetic quantum number, the ML, is equal to 0 as well. Before we move on to n equal to 2, however, I just want to remind you that 0, in a sense, has a code or represents a code. So that 0 is telling us that we're dealing with the S sublevel or S subshell. And also, the magnetic quantum number, the ML, tells us, in fact, the number of orbitals that exist in this particular energy level. And that one solution there says 1 orbital. Now let's look at the n equal to 2, the second energy level. And here we know that L can equal to 0, and L can also equal 1. If L is equal to 0, well then ML can only be 0. If L is equal to 1, we already saw it's minus 1, 0, and 1. And in terms of our codes, we know that the second energy level has both an s orbital, which you saw earlier is called a 2s orbital, and it has a 2p orbital. So the 2 in front of these letters is just saying at which energy level. Now you can see I've got 4 numbers in the right-hand side box. Each of those numbers represents a solution to the Schroedinger equation, in other words, an orbital. And so there are 4 orbitals in the second energy level. Now, you're wondering perhaps what the shape of a p orbital is. So I'm representing this on page 113, but I'm putting it all into one slide here just so you can see them. So we said that at L equal to 1, there's ML minus 1, 0, and 1. And this represents these different orientations. Those egg-like shapes, sometimes people think of them as dumbbells. They're oriented either in the x, the y, or the z axes. These represent boundary surface diagrams, the probability of finding the electron 90% outside the nucleus. One of the interesting things about a p orbital is that there's a chance of finding that electron both, let's say, above and below an axis. However, you'll notice that there's a node actually right at the nucleus. So there's no chance of finding the electron near the nucleus if it's in a p orbital. This simulation represents the 2px electron probability density plot. You can see that there's this dumbbell shape. You can see the nucleus in the middle here. There's also a node, so there's 0 chance of finding the electron right near the nucleus. However, there's a significant chance of finding the electron on the left-hand side and the right-hand side. This is adopting a certain orientation in space, which we will call x. If we now add another electron probability density plot for a p orbital, but let's say in the y or the z, you'll see that these electron probability plots lie perpendicular to the x. So here's a combination of a 2px electron probability density plot and a 2py. You've got the 2 dumbbells in a sense superimposed. The x dumbbell is sitting on the x-axis. The y is perpendicular to that, sitting on the y-axis. And one of the nice things about the simulation is we can separate the 2 different boundary surface diagrams. You can clearly see that you've got your y-axis dumbbell and you've got your x-axis dumbbell. So even in the hydrogen atom, an electron can be excited to a 2py or a 2px. In multi-electron atoms, there would be electrons that could exist both in the 2py and the 2px, and if they did, they would be sitting perpendicular to one another. We've just added the 2pz electron probability density plot. So now all the p orbitals with all the different orientations are represented. If I do my orbital separation, you'll see this more clearly. You can see that the 2px density plot sits perpendicular to the 2py. And if I just move around like this, you can see that indeed the 2pz is also perpendicular to all of them. So these 3 p orbitals potentially can contain the electron that's in the hydrogen atom if it's excited to a higher state, or again in multi-electron atoms, these p orbitals can definitely be occupied by electrons. Now, I think it's important to keep on going. If we get to the 3rd energy level, I think you'll start to see how these quantum numbers work with their allowed values. So at n equal to 3, L is equal to, and then it's 0, 1, 2, all the way up to n minus 1. So in other words, L is equal to 0, 1, and 2. For each L value, there are a set of ML values. So L equals 0, ML can be 0. L equal to 1, minus 1, 0, 1. And then L equal to 2, minus 2, all the way up to 2. So you can see now we have 8 different orbitals. The L equal to 0 corresponds to the S-type orbitals. L equal to 1 are those dumbbell p orbitals. And then finally, L equal to 2, as you shall see, represents the D-type orbitals. So let's fill this in our chart, just so that we have all that information in front of us. When n is equal to 3, the azimuthal quantum number can be 0, 1, and 2, and this corresponds to s, p, d type orbitals. Now here we would be writing 3s, 3p, 3d. Okay, so the 3 would tell us that we're on the third energy level. In terms of the ml values, well, once again, if L is equal to 0, ml is 0. If L is equal to 1, we've got minus 1, 0, and 1. If L is equal to 2, minus 2, all the way through to 2. And if you count up all of those solutions, well, then we've got 9 orbitals. Here are what the d orbital boundary surface diagrams look like. 4 of them are quite similar, and then we have kind of a bizarre one. Those 4 that look similar have been called cloverleaf-like orbitals, or boundary surface diagrams. And I want to point out something, because you can be asked to draw the boundary surface diagrams for certain of these types of orbitals, generally the simpler ones. You may notice that the D representation actually gives you a sense of how the boundary surface diagrams are organized. What you might want to do is actually put some letters on your axes. So if I set it up in this way, and I look at, let's say, the D, Y, Z, you'll see that the boundary surface diagrams that represent the D orbital, these are found in between the Z and Y axes. However, they're in the plane of the ZY axes. So this is why this one's called DYZ. In a similar way, if you look at the DXY, you can see the boundary surface diagrams also sit in the plane of the XY, but they're in between the actual axes. The same is true for the ZX. Now, I don't expect you actually to reproduce these boundary surface diagrams drawn like this. As you well know, I am especially no artist. Rather, you can redraw your axes in a way that make it a little easier for you to draw in these boundary surface diagrams. I'll show you some examples in our live session. And then lastly, I want to point out the dx squared minus y squared and the dz squared. In those cases, when the name of the orbital has the square in it, you can then see that in fact our boundary surface diagrams are sitting right on the axes. So the dx squared minus y squared, you've got those 4 cloverleaf-like boundary surface diagrams, and they're right on the xy axes. So in the case of the dz squared, there are boundary surface diagrams that sit right on the z-axis, and then of course we've got this weird ring that circles the nucleus. In some ways this kind of looks like a donut that's sandwiched in between by 2 eggs. Here's a simulation representation of the electron probability density plot for the 3dz squared. You may remember that the 3dz squared, in a sense, has 2 eggs sitting along the z-axis surrounded by a donut. Now right now it doesn't look like this. So what I need to do is turn it over like this. When you see the representation like this, it becomes a little easier to know that there's a node near the nucleus. That is a region of space where there's no chance of finding the electrons. So maybe we can zero in on that a bit. It's a little hard to see with all this other density plot going on. Sometimes it's easier to move back. Definitely you can see that shape of the 2 eggs plus the donut. Let's look at the shape of at least one other d orbital electron probability density plot. So here's a simulation of the 3dxy. As you may remember in our discussion, this 3dxy means that the cloverleaf shape of the electron density is sitting in the same plane as the x and the y axes. And the x and the y axes would be lying where there's this node. While they're sitting on the same plane as the xy axes, they are in between those axes points. So you may remember in the presentation, I was saying that if you had to draw this, you can very simply draw a y-axis and x-axis and simply show the cloverleaf sections as sitting in between the xy axes, and you can draw it quite easily. Lastly, just for completeness, I want to tell you about n equal to 4. And theoretically, we could go to n equal to 5, n equal to 6, but generally we go as far as n equal to 4 because that actually covers the sorts of orbitals that are used by most multi-electron atoms. Now, I think you can probably predict what this will look like. So n equal to 4, L can be 0, 1, 2, 3. For each L value, there is a particular ML value. So as you might expect, L equals 0, you've got ML equals 0. L equal to 1, minus 1 through to 1. L equal to 2, minus 2 through to 2. And then L equal to 3, minus 3 all the way up to 3. If you count the total number of solutions for n equal to 4, you'll see that in fact we have 16 different orbitals that are described. Here are what the boundary surface diagrams look like for these different orbitals. I haven't included this in your course pack. There's no way that you're responsible for trying to sketch out these boundary surface diagrams. And just for your general interest, here's an example of electron density plot for one of the 4f orbitals. This is the 4fz, x squared minus y squared. And you can see that the boundary surface diagram is quite complex. There's definitely these nodes in the region close to the nucleus and in between anything that might look like a clover leaf. A remarkable shape for the probability density plots, that is the region of space where we're likely to find an electron for the 4th energy level, and in particular for the quantum number L equal to 3 that represents these 4f type orbitals. So here now is a complete chart of principal quantum number n1 through to 4, the corresponding L values, and the corresponding ML values, and then also a listing of the number of different orbitals. Make sure that your own chart is complete like this, and then when you're working on some problems, you can always refer to the chart. And definitely in our live sessions, we'll now apply some of these bizarre rules and regulations about the quantum numbers to some actual examples.